everyone.
All right.
Let me turn on my writing instrument here. All right. This is a problem that I almost always get, is the sliding ladder.
The sliding ladder.
Yeah. You have a 13-foot ladder.
Okay.
And it starts to slide. The bottom starts to slide away from the wall. And the base of the ladder is moving in that direction at 3 feet per second. Hold on 1 second. This is my next appointment.
Yes, sir.
Hello. Hi, Russell. How are you? Okay. That's fine. You going to be here tomorrow morning? I'll see you tomorrow morning, Russell. You're welcome. Bye-bye. Sorry about that, Garrison. That's the one phone call I almost have to answer when it's my next appointment, because they're usually calling to cancel or change it or something.
Yes, sir.
I try not to answer phone calls while I'm in a session normally. So anyway,
yes,
back to this problem. So
right.
What is the rate of change of the top of the ladder?
So is that going to be, is this what we're figuring out, or are you just asking that?
This is what we're figuring out.
Okay.
In other words, this is a related rate problem. The top of the ladder is going to slide down the wall at a rate that's dependent on what the bottom of the ladder is doing.
That's right.
So once you recognize that it's a related rate problem, now let's try to set up an equation that models this picture. That's the next part to do whenever you're looking at a related rate problem.
Okay.
What equation models this picture?
So if we're,
What's this distance right here?
That's either 5 or 12.
It's x. Oh, and there is another part to this problem, but that distance is x.
Okay, x.
This distance is y. So now, what is the rate of change of the top when y equals 5? That's the question.
Okay.
I should have given you all of it, okay? In other words, the rate of change of the top is not going to be consistent as that ladder falls down the wall. It'll change depending on what y is.
Okay.
So whenever they're asking you about a rate of change of something, it usually almost always is at a moment in time. Hold on, let me close my window. We won't hear the band. I live near a high school. So it's always that. In other words, when they ask you about a related rate, it's always when y equals something or x at a given moment, what is the rate of change? And in fact, I didn't state it quite correctly here. When x is moving at 3 foot per second, yeah, no, I did. That's all you need. So what's the equation that models our picture?
So is that going to be y equals, or is that the right way to go about the equation?
Think of it as a right triangle. Use the Pythagorean.
Okay. X squared plus y squared is 13 squared?
Correct.
Okay.
Now, since everything is in rates, what does this mean? What is that? What is 3 feet per second?
3 feet per second, that is,
What's that equal to in terms of x's and y's? And
that's Rx.
actually, it's dx dt.
dx. That's right.
You know it's dx because it's x that's changing.
Over time, yes.
Right. And because it was given to us at 3 feet per second, remember that's velocity. And velocity is a derivative. It's the first derivative of position. So the information they gave us was dx dt. What are we looking for?
We are looking for dy dt.
Correct. Okay. So how are we going to produce some dx dt's and some dy dt's from this equation?
So
Think implicit differentiation.
implicit.
Almost all related rate problems are solved by implicitly differentiating. It's not always with respect to time, but most of the time it is. Okay, it can be with respect to anything. It can be with respect to an angle, to a theta, but most of these are time-based. So implicitly differentiate both sides of this equation with respect to t.
So are we going to have dx over dt squared?
Well, first of all, let's write it like this. That's what it means to differentiate the whole left side of the equation with respect to t. And over here, I got to do the same thing. What's the left side become?
The left side becomes dx squared over t plus dy squared.
Hold on. Start with the derivative, the outside derivative.
Oh, okay. So that's 2x.
And you got to follow with what? Because we're differentiating with respect to t, and x is not t.
dx over dt.
Okay. Keep going.
Plus 2y times dy over dt.
Correct. And what about the other stuff?
That's just going to be, wait a minute, that's just d over dt, right? Or
Zero. In other words, the derivative of a constant is 0. 13 squared is a constant.
that's right. I keep on confusing the the derivative of a single variable is that, like, just x. That's
whatever
the
the
coefficient
of that variable is.
And then a coefficient is just 0.
Yes, all numbers, all constants. If they're not variables, they're constants, and derivatives of constants. Remember, a constant is a horizontal line. So the derivative is the slope of the tangent line, which is 0.
Yes.
And you could say, well, do we need to follow that with a d something dt? And no, we don't, because 0 times anything is 0. So once you get 0, you don't need anything else over there.
That's right.
Okay. Now, they want to know what the rate of change of the top is, which is dy dt, when y is 5. So what's my next step? In other words, if I look at this equation right there, I need to know x. I need to know dx dt, which they've given us. I need to know y, and they're asking us to solve for dy dt. So what's the next line going to read?
dy dt, 2y dy over dt is equal to 2x dx over dt.
To equal to minus 2x.
Minus.
But rather than do that, let's just leave it. In other words, you don't need to solve that equation. So all you need to do is start substituting.
Okay.
Do we know what x is when y is 5?
12.
Okay, so we got 2 times 12. Do we know what dx dt is?
3 feet per second.
Plus or minus?
Minus.
No, it was a trick question. It's plus because x is increasing. The amount of distance from the wall is getting bigger.
So if the absolute value on the coordinate plane is increasing.
No, it's plus 3. If it were getting smaller, if the bottom of the ladder was moving towards the wall, it would be a negative, whatever rate it was.
Yes, sir.
So the way you figure out whether it's positive or negative is based on whether the x is changing and getting bigger or it's getting smaller, and the same thing with the y. So what's y?
Y is 5.
And that's what we're trying to solve. Now the math gets particularly easy.
I see.
24 times 3 is 72. It's a negative 72 divided by 10, right?
– 7.2 is dy dt.
And it is supposed to be negative because y is getting smaller.
That's right.
As the ladder slips, the top comes down, y is, and you gotta check these signs, make sure you're using the correct sign, because that can mess you up a little bit. Okay?
Yes, sir.
So that's how we do a related rate problem. In other words, you figure out what they're giving you, which is a derivative, and you figure out what they're asking you, which is a derivative, and then they specify the moment in time that they're asking you this. Because when y is 3, that rate will change. It'll no longer be minus 7.2. What are the units on that number?
Feet per second.
Yeah. So the y is falling quite a bit faster than the x is sliding. X is only moving at 3 feet per second. The y is moving at, its speed is 7 feet per second. Velocity is negative 7. That's the difference between speed and velocity. Velocity always has a sign. If you're moving to the right, velocity is positive. Or if you're moving up, velocity is positive. If you're moving down, velocity is negative. If you're moving to the left, velocity is negative. And that's why this problem's a little bit tricky, because I don't blame you for thinking that dx dt was negative because it's moving to the left. But these related rate problems, it has everything to do with, is x increasing in size or decreasing in size?
Yes, sir.
All right, let's try a slightly harder one that we talked about last week. Okay, we have water runs into a conical tank at 9 cubic feet per minute. The tank stands point down, like that.
That's right.
The tank has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep?
Rising or sinking?
Well, water is being added in this case.
Oh, okay.
So, all right. So first of all, let's identify what this 9 cubic feet per minute is. It might be easier to identify the equation that models this first.
Okay.
What is the equation of a cone? And we're interested in volume. In other words, that's a dv dt that they've given us. And
all right.
you can tell because volume is in cubic feet. So when they're talking about cubic feet per minute, they can't be talking about a dH dt or a dr dt. They're talking about volume changing. So that thing has to be dv dt. And it's plus because volume is getting bigger as water drips into this tank. Now, let's put our equation in there that governs this situation.
All right. Volume equals pi r squared times height divided by 3.
Whoops. Now, this particular problem, the cone problem, is you're going to get it numerous times in calculus. And that's why I wanted to make sure I taught you how to do it, because it's just slightly tricky. Okay? I did it wrong last week. I went ahead and implicitly differentiated that equation relative to t. And
Okay.
there's an intermediate step that we need to do here. What we would like to do is have volume all be a function of one variable. Right now it's a function of 2 variables. It's a function of radius and also height.
Okay.
Can we make it a function of 1 variable?
Is that just going to be volume, or can we not?
How is radius and height related?
They are inversely related.
Well, if you look at these 2 triangles that I drew, you have that triangle,
Okay.
and we have that triangle.
Okay.
What is the relationship of those 2 triangles? What kind of triangles are they?
They're similar triangles.
Okay. So what does that tell us? It tells us if I let that be x and that be y, we know that in the big triangle, the height is 10, the radius is 5.
Yes, sir.
So what's true in the little triangle?
The height is 6.
Well, we can say x is to y as what? In other words, think about 2 similar triangles and how you can make ratios comparing them.
X is to y as 10 is to 5.
As 5 is to 10.
5 is to 10.
Okay.
Yeah.
And here, let me relabel this because it's not quite clear. What really is y is this amount. Let's hold on. This amount from there to there is y, and that's x.
Yes, sir.
And that's really our equation, because the water level is at 6 feet. So we're really dealing with that small triangle. But I know that the bigger triangle has a ratio of 5 to 10 between its top radius and its height. So it has to be the same ratio for x to y. Okay.
Yes, sir.
Y is h, and x is r.
That's right.
So r, or let's solve for h. H equals 2x.
That's right.
Or, excuse me, 2r. I'm going to use the proper variables. So now let's go back into this equation and rewrite it all as a function of r. So
Okay.
pi r squared, h is 2r. Now we can differentiate it with respect to t.
Okay.
So what's the next line?
So this is going to be both sides d over dt.
Okay, that's what the left side ends up being.
Okay. So
Let's go ahead and combine those, and let me put the 2 there and add an exponent and erase that 2r.
all right.
To make it a little easier to differentiate.
All right. So that's going to be, oh boy. So that's 0, or that's 1. So we're going to have 3r squared in there.
Hold on. Start with the exponent.
3
Times.
times, oh, that's right, 6 pi r squared.
Divided by 3 makes that 2. In other words, 6 over 3 is 2.
That's right.
And then what else do I need? Because I'm differentiating with respect to t.
So that is r's and t. So that's dr over dt?
Yes. Because I ran into a variable that is not t, I always have to follow its derivative by dr dt.
That's
Just
right.
like v is not t either. So when I differentiate v, I get 1 times dv dt, which is how I get the left side of this equation.
Yes, sir.
Now, the full question says, I'll go back and read it. How fast is the water level rising when the water is 6 feet deep? So what are they asking for?
They are asking for how fast is it rising when it's 6 feet deep. So they're asking for the increase in height, so dh over.
Yeah, so let me go back here. I can realize right now we're not going to have a dh dt. So let's just back up. Since they're asking for dh dt, how about we write this formula in terms of h instead of r?
All right.
So r equals h over
1/2. Yeah, h over 2.
So I'm going to substitute that for r. Now let's do the whole thing again. So it's h over 2 squared times h, all divided by 3. Which means it's pi h cubed, all divided by 6. So that's what v is as a function of h. And can you see why we would rather have it as a function of h? Because we're going to end up with a dh dt by the time we differentiate this. So let's go back and differentiate this. It's still dv dt because that's what they've given us, 9 cubic feet per minute. That's a dv dt. Okay, now plug in. Well, first of all, excuse me, implicitly differentiate it.
All right. So we're going to have 3 pi h squared over 6. So that's going to be pi h squared over 2. And then dh dt.
Now we're talking. Now we've got the thing they're looking for, that right there. So what's the next step?
Plug in.
Okay, hold on a second. Let me erase some of this. Go ahead.
All right, so we have dv dt is equal to 9 cubic feet per minute.
Okay.
And then we have the height is 6, right?
Right.
Is 6?
Pi 6 squared.
36 pi over 2, so we can divide that, and that's 18 pi. And then we have dh dt. So we have pi over 2 equals dh dt.
Not pi over 2. Be careful.
Wait, 1 over 2 pi.
There you go. It's not, actually, it's quite frequently that pi ends up in the denominator. Yeah, that is the answer. Is it plus or minus? What did it come out to be here?
Sir?
What did it come out to be?
I got it as positive, right? Because it's
Is that correct? In other words, that's the first check you want to do when you get done. Does the sign of your answer make sense logically? Is dh dt increasing or decreasing?
It is. So for it to be increasing, it just has to be positive. It doesn't matter if it is
getting bigger. In other words, h is currently at 6 feet. Where's h going to be 5 seconds from now? Bigger than 6 feet, right?
Okay.
In other words, the height is going up on this cone as water is being added to it. The reverse thing would be water is leaking out of the cone. And then, of course, dv dt would be a negative number. And dh dt would also come out being a negative number.
That's right.
Okay. So that is our answer. And curiously enough, notice that that has an irrational denominator and you can't rationalize it. It's impossible to rationalize. There is no way to rationalize pi being in the denominator. So
Yes,
irrational denominators certainly exist in math and real life. And I don't know why mathematicians have spent as much effort as they have teaching people to rationalize fractions that have irrational denominators. Because it's not useful in trig, and the moment you get real life problems, it becomes a bit moot. Okay? So
yes,
remember this cone problem. You will do this again. You'll be faced with this on a test. Okay? And the trick of the cone problem is to turn either r into a function of h or h into a function of r based on two similar triangles. Just remember that part, because that's the tricky part.
Okay. Two similar triangles.
Yeah. And which is not immediately obvious. In other words, it's useful to have had a few of these that you've practiced on so that you know this is a big step right here, relating those two triangles. Because that allows you to define r as a function of h or h as a function of r.
Yes, sir.
Okay. Now, I'm going to go back and try to do this one again. That equation, first of all, is x squared minus 2. Nope, I got it backwards again. That was my problem before. It's actually 2x minus x squared. Okay?
Yes, sir.
Why is it not x squared plus 2x?
Because it's a phase shift, not a vertical
Well,
shift.
it's a parabola because it's a quadratic, but it's a parabola that opens down. In other words, and I do know what's the two zeros of that parabola.
0 and 2.
Right. So now when I ask the question, what's the biggest area you can fit in that parabola under that function?
Okay.
Okay. This gets particularly tricky. Let's start with, what is that point right there? What are you going to call it?
Are we going to call that X?
Yeah. Yeah. Well, that's not immediately helpful. What's this point right here?
Y.
Correct.
Okay.
In other words, if you're on that graph, that's the y value. Okay.
That's right.
Still not that helpful. Here's the secret on this one. There's usually a secret on these. By secret, I mean a non-obvious step. What's that distance right there?
2 minus X.
If that's 2 minus x, what is this distance right here?
That's 2 minus X as well.
Yeah, and I don't know. You can kind of see why they have to be both the same. Parabolas are always symmetrical about their axis of symmetry, so that makes them the same. And we know intuitively that this rectangle the middle of it has to go through the axis of symmetry. Okay?
That's right.
Okay. So our next thing is to define this distance right there. Because after all, we're looking to maximize the area. So we need what the base is. In other words, what the base, the area function, is length times height, right?
Yes, sir.
Okay. If we want the area, well, let's just call the area function. What's the length
The length
of that rectangle? What's the length of that rectangle? I haven't labeled it because you gotta use the two sides of it.
So are we just going to have the length be the...
What's the length?
Is that
The length is 2 minus those little pieces, right?
Yes, 2 minus 2 times 2 minus X.
There you go. That's the length of that rectangle. What's the height?
That's Y.
Okay, let's make it a function of x.
So, it's the same thing.
What's y equal to? What's that function up there in blue? What's y equal to?
Oh, 2x minus x squared.
That's what y is. It's whatever the function is. So this becomes what? 2 minus 4 plus 2x. So that becomes 2x minus 2. So that's the length. 2x minus 2, right?
Yes, sir.
times the height, which is 2x minus x squared. So now I can say that's the area function as a function of x.
Yes, sir.
Now what do we need to know? Well, what do we need to do next to maximize that the area of that rectangle?
Wait, was it we find the first derivative of it?
Yeah, but we can make it a little bit easier if we multiply these two things together. Okay. So area of as a function of x equals, what is that? 4x squared
minus
2x cubed
minus 4x minus is that 2x squared?
The last one is plus 2x squared.
Plus 2x squared.
Okay. If we simplify all of that, we've got a minus 2x cubed at the beginning. We have a plus 6x squared minus 4x, unless I made a mistake in my math.
That's what I got.
Okay. So that is the area as a function of x simplified. What are we going to do with that?
All right. So we find the first derivative.
Okay. So what's a prime of x? What is the derivative function?
Negative 6x squared plus 12x and then minus 4.
What are we going to do with that?
We are going to find the roots.
We're going to set it equal to 0 because we're looking as to where the first derivative has a horizontal tangent line.
Yes, sir.
Okay. In other words, this equation that's graphed here, that's the equation. That's not the first derivative equation. The first derivative equation would be the graph of that bottom formula. Okay. So
yes, sir.
Let's erase some of this stuff so that I can finish the math here. Going blue. So what should I write for my next line?
Oh wait, you already said it equal to 0?
Right. In other words, I'm working with this right here. The next thing to do.
We can factor out a negative 2.
Yeah.
Do we want to do that?
I'll go ahead and do it. So now we have 3x squared minus 6x plus 2. Did I do that right?
Yes, sir.
Equals 0.
Yes, sir.
Now, what next?
We try to factor it.
Okay, I made up these numbers, so I can't promise that this is going to be a, let's see, let me think for a second.
Yeah, we may have to do.
It's going to factor nicely, does it?
All right, so we're going to use the quadratic formula.
Correct.
So 6 plus or minus the square root of 36 minus 4 times 3 times 2 all over 6. So that's the square root of 36 minus 24, 12 to root 3. 6 plus or minus 2 root 3 over 6. 1 plus or minus root 3 over 3.
Okay, let me go back a second here. Let's see. That's 36 minus 24, right?
Yes, sir.
So it's root 12. And root 12 is actually 2 root 3.
Yes, sir.
So there's my answers, and I can simplify it, but not to 1. Let's simplify it by dividing top and bottom by 2.
Okay.
So we get 3 plus or minus root 3 all over 6. I like this answer better because that's the typical format for the quadratic formula.
Yes, sir.
Is a numerator that has a plus or minus between an irrational number and a whole number, all of it divided by a real number.
Yes, sir.
So we've just solved for x and we've got 2 solutions. Well, I think that makes sense. In other words, there's one solution, the minus part of that, and there's the other solution, the plus part of that. Because notice how that first point is also x.
Yes, sir.
So we've got, let's see, we've got x equal 3 plus 1.7 over 6. And we've also got it equal to 3 minus 1.7 over 6. Both of those are positive numbers, which is what our picture indicates. So this first x is going to be like 1.3 divided by 6. And the second x is going to be 4.7 divided by 6. Approximately. In other words, I did convert. That's not the way to give the answer. The way to give the answer is over there, using the radical sign. Only reason I converted the decimal is so that you can see that the whole picture makes sense now.
Yes, sir.
Notice also that we do not have a square.
Oh.
I don't think. Maybe we do, actually. Let's see. What is x?
So we subtract
Yeah, the first
3.
x and the second. Yeah. So we end up with what? There's our base. That's the length. 3.4 over 6. And our height is going to be 2 times 4.7 over 6 minus 4.7 over 6 squared. Right offhand, I don't know. I don't think it's worth doing all the arithmetic to see if those two are the same number, especially since I've rounded off. If they were the same number, it should come out to be close enough that it would be approximately equal. So it might be a square. I don't really care. That's not the way you want to do the problem. You want to do the problem as an optimization problem.
Yes, sir.
Where you can make an area function that is all a function of one variable. It doesn't really matter whether it's x or y. In this case, it made more sense to make it x. But you can see that this was quite tricky. Not altogether that different than the original one, which is this one.
Yes, sir.
I said that. Well, we did the same thing here. It's just that that point was x. This point has to be negative x, so we immediately knew that the length of the rectangle was 2x. And this equation was y equal 3 minus x squared. Again, you need a negative sign in front of the x squared for these functions if you're looking at a parabola that opens down. Okay, so the height in this case is 3 minus x squared. So the area function as a function of x is 2x times 3 minus x squared, and then you finish the problem exactly the same. Okay,
yes,
we did the last one. In other words, we multiply those two things together, take the first derivative, set it equal to 0, solve for x. The tricky part about the previous problem, the one we've been working on, is you needed to figure out what that was, that distance right there. I guess there may be another way to do that other problem, but every time I've seen it in a textbook, this is the way I showed you to do it, is the way you have to do it, which is a little bit thinking outside the box. It's not obvious that you would need that little distance right there. In other words, on this problem, I don't need that because I know what my base is. My base is 2x, or my length of the rectangle. Okay?
Yeah, sir.
All right. Look in my book and see if I got a good one we can do in 12 minutes. Have I done the cops racing towards an intersection with you yet? Let's do it.
Not yet.
That is similar to the sliding ladder, but not quite the same. We have a cop car. But, however, this is quite the real life problem.
All right.
So what you have is a robber car on the x-axis heading in that direction. You have a cop car chasing them that has to go to the intersection. Can't just go across the field straight at them. It's got to go to the intersection first, turn left. Okay?
Yes, sir.
We know the speed of the cop car. 60 miles per hour. They can read their own speedometer. They also have a laser gun pointed at the robber car. And
okay.
They can see that their laser gun is showing a speed of, we'll say 40 miles per hour. Again, I'm just making up these numbers. What they want to know is how fast is the robber car going?
Okay.
So let's define everything. What have they given us?
So this is this similar to like a sliding ladder?
It's similar, but this time the sliding ladder always had a fixed hypotenuse. It was always 13 feet long. In this case, that's not the case with this one. Look at the triangle and think right triangle.
Yes, sir.
So what is 60 miles per hour?
That's dy over dt. dy dt, yeah.
Is it plus 60 or minus 60?
It's the constant rate they're traveling at, but they're getting closer to the origin. Does that have anything to do with it?
Yeah, what is y doing? Getting smaller as they go towards that intersection or getting bigger?
It's getting smaller.
So it's negative.
Okay.
Negative 60.
So it is. Okay.
What's 40? 40 is how fast the robber car is separating from the cop car.
Okay.
It's not the speed of the robber car. It's just what their laser gun is showing.
So
Because
40
they have the
is,
ability to point a laser at that robber car, and that'll tell them how fast the robber car is separating from the cop car.
so 40 miles per hour. Is that going to go along the hypotenuse?
Yeah, we'll call it Z.
Okay, DZ.
dz dt equals 40. And that's a plus. Notice why it has to be plus.
Because they're moving along the x-axis further away.
To the right, and the cop car isn't making any motion at all. So any separation that's taking place is increasing Z.
Yes,
So until the cop car hits the intersection, the robber car is going to keep going to the right.
that's right.
So dz dt is a positive number. And here's what they want to know. Speed of robber car when the cop car is 6 miles from the intersection. And the robber car is 8 miles from the intersection.
Okay.
So we've got all of our givens and our instantaneous point in time. So let's write an equation. You always have to get to that point in these related rate problems, where you write an equation that models your picture.
Okay. So we're going to try to put this all in terms of x.
Well, let's first of all just model the picture.
Okay.
In other words, that's x, that's y, and that's z. Write an equation that relates those.
Z squared equals 6 squared plus 8 squared.
Write it as variables.
X squared plus y squared equals z squared.
Because the next step is to differentiate it, not to plug it in.
Yes, sir.
In other words, everything they've given us is some d of something over dt. And what are they looking for? They're looking for dx dt. That's what we're trying to solve for. That's the speed of the robber car, is dx dt, right?
Yes, sir.
Okay. So what's the next step in this equation?
Man, what's the terminology for it? It's
implicitly.
Implicit. In terms of dt, right?
Correct. Because they gave it to us in terms of dt. They give us this in terms of dt, and their question is in terms of dt.
Yes. All right. So we're going to have 2x times dx over dt plus 2y times dy over dt equals 2z times dz over dt.
Now, if you look at that equation, we need x, we need y, we need dy dt, and we need dz dt, and we have all of those.
That's right.
So we're trying to solve for that. So let's plug in everything else that we have.
All right. So x is 8. It's going to be 16 dx dt. Y is 6. And dy dt is negative 60. So that's 12 times negative 60 is equal to dz dt is 40, and z is 6, 8, that is 10. So 400.
Okay. So there's our equation. We're only missing one variable. Should be able to solve for dx dt. And hopefully will come out positive. Comes out negative, we've made a mistake. Because we know that dx dt is positive. So what do we got? We got 16 dx dt minus 720.
Yes, sir.
Equals 800?
400.
2 times 10 times 40?
Oh. Yes. Yes, that is 800.
Okay. So dx dt, 1520 divided by 16.
95 miles per hour.
Okay. Cool. Rubber cars, that cop car better speed up. In other words, the cop car now knows how fast the robber car is going, right?
That's right.
So they're not going to keep going 60 miles an hour. They're not going to have any chance of catching it. They got to get to that intersection and then speed up to above 92 miles an hour to catch up.
Yes, sir.
So that's a related rate problem, where the hypotenuse of the triangle is a variable that changes length as the cars move. Unlike the ladder, whereas the ladder is falling, the ladder is always a 13-foot ladder. Well,
yes,
Z is only equal to 10 at this moment when Y is equal to 6 and X is equal to 8. That's the only time Z is equal to 10. 5 seconds from now, Z will be a bigger number than 10.
Yes, sir.
Okay. Those are your standard related rate problems that you will run into repeatedly. I don't know about the cop car chasing. That's my funnest one. That set off a light bulb in my head when I was reviewing calculus and I saw this problem. It all made sense. And then the ladder problem helps get the signs right, because it's not the direction they're going. It's whether X and Y are getting bigger, getting smaller. What's Z doing? That's what determines the signs on those derivatives.
Yes, sir.
Okay. That probably is going to cover our related rates. And I may find some optimization problems to discuss, but we'll go beyond this next week. Where are you at in your math class? What are they covering now?
So far, it's just been a lot of trigonometry review, inequalities, stuff like that.
Okay. Good.
All right.
Garrison, have a good one. I'll talk to you next week.
Yes, sir. You too.
Bye-bye.